Hey, ladies and gentlemen. Welcome to 14.1, which is entitled Periodic Motion, Springs and Pendulums. I'm sure you guys have had experience in your life with a spring or a pendulum, like you squeeze a spring, you stretch a spring, or you set a pendulum in motion. And we're going to be talking specifically today about, are there ways to predict how far a spring will stretch if you put a certain amount of force on it? If a pendulum is this long and it's got this much weight on it, what's the frequency with which it goes back and forth? And there are ways to predict how pendulums and springs work. So let's get started. The first thing that I want to talk about with springs is this thing called Hooke's Law. Hooke's Law is an important part about springs because it tells you how far the spring will stretch if you put this weight on it. If I have this type of spring, how far will it stretch? This F stands for force. The K is what's called the spring constant. The units of K are newtons per meter, and X stands for distance. For instance, if you had a spring that was 100 newtons per meter, if you put 100 newtons of force on it, it will stretch 1 meter. 50 newtons of force on it, 0.5 meters. So I have a website that I found that I thought was pretty interesting that deals with Hooke's Law here. And you can kind of see it in action. It's got some virtual springs. You can take them off, drop them down. I put 50 grams on this one, 100 grams on that one, and then nothing on this one. And you can see that when I put 50 grams on this thing, it stretches about, from the bottom of my spring, 0.5. And then when I put 100 grams on it, so I double the amount of mass, I should double the amount of length. I'm at 10 centimeters. So here I'm at 5 centimeters, here I'm at 10 centimeters. And springs have what are called a restoring force. So if I pull this down, there's an upward force provided by the spring that wants to restore it to its original spot, and it's going to vibrate like this. Now, if there's more friction or less friction inside the spring, and I can actually control that over here, if I have lots of friction, you'll see that that thing dampens pretty quickly. And if there's absolutely no friction, this thing will just go forever, bobbing up and down like this. And you know, in real life, it's never none, and it could be lots, but the thing will eventually die down. Now, I can actually show the energy of this, which is kind of neat, like of spring number 2. I can show how much energy. Now, if I take away friction, when I pull this, I can give it more energy. And you'll see that I'm giving it potential energy right now. And it's got some potential energy provided by gravity because it's a certain distance above the ground. So when I let this thing go, holy cow. It cycles between potential energy and kinetic energy. I wonder if I can slow it down just a little bit so you can see. But always, potential energy plus kinetic energy plus all three of these are going to add up to your total amount of energy. Pause it at the very bottom. It's stopped right now, so there's no kinetic energy. It still has some gravitational potential and potential that's stored in the spring. Slow it down. Now all that gets lost to thermal energy. So when you have friction, you have some thermal energy also. So here's our first sort of example problem. And if you can figure out the potential energy stored in a spring, if you pull a spring, how much is stored in it, or if you compress a spring, how much is stored in that. It's 1/2 the spring constant K times X, the distance that you pull it squared. So here's our first example problem. It says a spring stretches 18 centimeters when a bag of potatoes weighing 56 newtons is suspended from its end. So this thing's being pulled down at 56 newtons, and the thing stretches from its neutral position 18 centimeters. So determine the spring constant. F equals negative K X. So the force I'm applying to this thing is 56 newtons. I'm looking for the spring constant, and the distance that we're stretching it is 18 centimeters, or 0.18 meters. So to figure out my spring constant, now this negative just represents that it's a restoring force. So the negative really doesn't make any difference inside of here. If I take 56 divided by 0.18, and that's 311 or 310. Now that's newtons per meter. That's how much it takes. If I wanted to stretch this spring right here 1 full meter, I'd have to exert 310 newtons on it. And part B says how much elastic potential energy is stored in this. The potential energy is that 1/2 kx squared. So 1/2 times 310 times 18 or 0.18 squared. So you just plug that in. So 0.5 times 310 times 0.18 squared. You get 5.0 joules of energy. So springs, pretty straightforward. You pull them, they want to pull you back. You push them up, they want to pull you back down. All governed by Hooke's law, which states that springs, the farther you pull them, the more force is on them. The next thing, pendulums. I have a couple of videos here one video that really inspired me. It's in the back of my classroom right now. This is down at Arizona State, and this is exactly the video that gave me the idea. And mine is patterned exactly after it. I patterned it by watching this video, counting how many times, and it's really mesmerizing to watch this thing happen. This is what a finely tuned wave pendulum will look like. And it takes 1 full minute for this thing to complete its cycle. That's actually 30 seconds into it, not right there. I'll tell you exactly when 40 seconds is too, right there. 20 more seconds, you'll see this thing will have completed an entire cycle, and they'll all be back to the starting position. Now, see it? Very amazing. We don't have to watch it through its second cycle, but I'll leave a link to it so you can check it out. Pendulums. Pendulums work just like you've always seen them. Pull a mass up, and you let it swing. Now, they don't swing forever on Earth. It depends how much friction. It turns out I've got lots. If we take friction all the way away, you pull this thing up here, let her go, and it will never deviate. It will always go back to its original spots here. If I give it more friction, it will just dampen it. And you can see that it's starting to get less and less with each one. I give it lots of friction. It goes like this. Now, I'll just go back to having none for right now. I'm going to increase the mass, and I want you to watch what happens. I'll increase the mass from 1 kilogram to 2 kilograms. And you'll notice that the period of this pendulum swinging doesn't change. Going back and forth, I make it lighter. It doesn't swing any faster or slower. But the thing that makes a difference, it will swing longer if you've got more weight on it. So if I increase friction here, you'll see this thing will die down like almost immediately. I increase the mass, go back here, it's going to swing for a lot longer because of the mass. Go back to my friction. Now you maybe have noticed the only way to change the frequency of a pendulum is to change its length. And that's what this video was trying to show you, that some of these pendulums have different lengths. When you look at this thing, let's see if I get a good picture of it. Some of these have different lengths. The ones on the far right of the video have smaller lengths, so you lengthen this thing, you make it shorter, you'll see that it swings much more frequent than if you make it much longer. And if any of you have like grandfather clocks at home, you'll notice at the very bottom of these things there's a little nut that you can turn, So you can make it shorter or longer by just a little bit, so you can adjust the frequency of swinging, and you want it to be 1 second. So just a couple other things I can show you on here. We'll make it a little shorter. Play it. This is what it would swing like if it was on the moon, if there's less gravity. This is what it would swing like if it was on Jupiter, underneath a lot more gravity. And if you had 0 gravity, guess what it would do? You're right. It would just hang there. If I could stop it at just the right spot, like right. No, nope, it's going to keep going. And go right on around. Pendulums. Back to them. There's a way to find the period of a pendulum. The T stands for period. 2 pi, the square root of L, which is the length of the pendulum, divided by G, which is how much gravity it's underneath right now. So a pendulum with a length 36.9 centimeters has a period of this. What is the acceleration of gravity at that pendulum's location? So I'm going to grab this equation here. 2 pi square root L over G. And that's going to equal the period of the pendulum. So we're just going to plug in a bunch of numbers here. It's got a length of 36.9 centimeters. So 2 pi square root of 0.369 divided by 1.22. Well, we're looking for gravity, and then this is 1.22 seconds. So you basically solve this for the letter G. Pull out my calculator, and I'm going to take 1.22 and I'm going to divide by 2 pi. Make sure I put the 2 pi in parentheses. And I'll square it. And then I'll take 0.369 divided by it. And I end up with 9.79 meters per second squared. And we all know that gravity is 9.8, so this is kind of neat. It's a way to figure out how much gravity you're underneath by counting what the period is, how long it takes to do one back and forth. The easiest way to do it would be actually do it 100 or 10 times, count those, and divide by 100 or 10, and you can actually figure out the acceleration due to gravity wherever you're at based on that pendulum. So that's 14.1, periodic motion. Periodic motion means motion that repeats itself over a certain period, like springs bobbing, pendulums swinging. We can find springs through Hooke's law, and you can find pendulums through, I don't know what the name of this law is, it's just an equation that dictates the period of a pendulum.